To start off, any questions on the project? I have one person has sent me a paper. Thank you, Tar. So as time goes on, so this is going to be a continuing thing that I'm going to do every year, right? Because this is a multi-year project. So for you guys, it's really trivial because there's lots of data out there for simple mixtures. I fear for the people in 4 years that have to be scrounging for these really esoteric mixtures and things like that. But for right now, it should be relatively straightforward. I don't think it's a huge rush because I'm sure no one's going to be submitting their project, next week. But I'll be uploading the template into the project section. But I won't send out an email. I'll just put it up there. So to wrap things up, we're basically going to have the project, one final homework assignment focused on statistical mechanics. The final exam is on the 12th of December. So it'll be 2 hours, but I'm going to write the exam like a normal kind of length exam, which means that I won't be able to cover everything that we've talked about in class, but it's going to be the greatest hits. So I think you can assume which areas we focused on a little bit more than others. For example, vapor-liquid equilibrium, non-ideal, phase diagrams, cycles, and then stat mech will probably be 30 to 40% of the exam. Maybe closer to 30%, right? The reasoning for that is I don't necessarily know if a 100% dedicated stat mech course is the best for a chemical engineering graduate program, because there's only a subset of people who will actually use stat mech. But I think what's really important is I just want everyone to understand the principles of what we're going over here, right? Because understanding the principles of how we translate macroscopic processes to microscopic behavior of molecules is going to be critically important, particularly for most any scientific discipline that you guys will be working in. So I don't consider what we do here is extremely rigorous for stat mech, but it's important that you understand the principles. So go through and understand all the examples. For the homework, make sure that we understand the examples there. Any questions between now and the end of class? I am planning on having class on Wednesday next week before Thanksgiving.
When is the due date for the project?
Project due date Tuesday is when you have to select your system mixture. And then on the 9th, which is, I guess, the day of your guys' fluids final, that'll be when the full project is due. Oh, you may have missed the handout.
Oh, okay.
Okay. No questions. Uh-oh. Let me fix that. So today what we're going to do is we're going to go over a phase transition lattice model. Now, lattice models are one of the most intuitive applications of statistical mechanics. The reason for that is that entropy is extremely hard to estimate. But with a lattice model, what we're saying is that we're only going to allow particles to fall into positions on a one-dimensional, two-dimensional, or three-dimensional grid. Now what this allows us to do is then we can calculate the total number of configurations of the system because you're locking in the real space positions that the fluid molecules or the gas particles can be in. So lattice models are going to be one of the most sort of interesting applications of stat mech that we can do. So when we want to look at a phase transition using a lattice model, so this is going to be our source to estimate the entropy. We need a source to estimate our internal energy of the system as well. So if we're looking at a fluid-fluid transition, or some sort of a gas-liquid transition, right? Phase transitions are a balance between the internal energy, or enthalpic contribution, and the entropic contribution. So, if all properties were controlled by the internal energy, what we would expect to see is that from a binary pair potential, let's say we follow a 6-12 Leonard-Jones shape, the minimum energy configuration of any collection of particles would be that everyone is separated at exactly this potential energy minimum well depth. So if internal energy controls the phase transition, that would mean that all of the particles in the system would be in what I would call the condensed phase. Now this could be a solid or it could be a liquid, but it's not going to be a low density fluid like a gas. So that means that the driving force for the system to be in a low density phase is going to be the entropy itself. Now if we model the entropy with a lattice model, effectively what this is saying is that if you have a low number of particles, right, if n is much, much less than what we'll call v, which is the number of particles, number of boxes, let's say bins, there we go. That would mean that you have a tremendous amount of entropy that would be promoting going into the non-condensed phase. So what we need to consider in this lattice model is a way to model the internal energy and a way to model the entropy, put those two forces together and see what kind of outcome we get. So I'll kind of jump ahead a little bit, but effectively what we're going to be more or less doing today is deriving a sort of like the van der Waals equation of state. It'll look very similar to our final conclusion. Okay, so in the case of entropy, in a lattice model, if the energy is constant across all configurations of the system, what that means is that we will go from the microcanonical ensemble and the canonical ensemble, and that will take us into the microcanonical ensemble. Now, if you recall, the microcanonical ensemble is simply the summation of all of the possible configurations of the system. So with that case, that means we could write the entropy using the Boltzmann entropy equation, looking at it as simply the natural log of the partition function. Now this is only appropriate if we have all states of the system having constant energy, which will make an assumption so that can actually be valid. So for this particular system here, for an m by m lattice, we're going to call the volume is equal to whatever this lattice parameter is q. We're effectively going to make it infinitely sized. We're going to make it so it's arbitrary of the system size. And big N is equal to the number of indistinguishable particles. Such that if we use combinatorial statistics, we have a grid with effectively V vacant sites and N particles to fill them where they are all indistinguishable. The number of ways that we can combine this system is going to be given by this expression here. This is going to be our microcanonical partition function. If we can demonstrate that every single configuration of the system is going to be having a constant energy. So this is going to be if energy is constant. If energy is not constant, that means we're going to be in the canonical ensemble where we have to consider temperature. We'll have to consider that the higher energy states are going to be less probable. But in this case, we're actually going to make the assumption that all states are equally probable. So how we do this is we use something called a mean field approximation. Now this is more or less the approach that van der Waals took when he derived the van der Waals equation of state, assuming that the effective pull from one molecule is going to be a function of the density of the fluid overall. So we're basically going to be kind of smearing this out and coming up with an average density of the system and then saying that all particles have that same energy of the system. Okay, so let's look at that approximation here, this mean field approximation. So what we're going to say is we're going to define some coefficient epsilon. This is going to be the energy of interaction between two particles in the system. So if we have a one-dimensional array, and let's say we have a configuration like this, we're going to say that we're going to come up with a parameter called z. We're going to call it 2. Z is the number of potential neighbors. And that the energy of each pair of interactions is going to be given by this epsilon coefficient, which means that the internal energy of this system here, U, is going to be equal to minus 2 epsilon. Now we add the minus to indicate that this is an attractive interaction. You always want to go to the minimum free energy. Now it's a little bit always confusing, but when you look at the energy of let's say a Leonard-Jones fluid, or a fluid that follows a Leonard-Jones type intermolecular pair potential, your energy is always going to be negative unless you're basically overlapping. But negative energy is good energy. That means you're giving it off to the system. All right, so 2 dimensions. In this case, z is equal to 4, and based on the configuration that I've described here, we have 1, 2, 3, 4 pairs of interactions. That means our internal energy of this particular configuration would be minus 4 epsilon. In 3 dimensions, it's very difficult for me to draw this very precisely, but you can hopefully see the extension. In 3 dimensions, z is going to be equal to 6. And if you have a fully sort of condensed system where all the sites are occupied, in that case, the internal energy would be minus 6 epsilon. So, to generalize this, what we're going to write is that the density of the fluid is going to be equal to the number of particles over the system volume. It's the fraction of occupied sites in this lattice-based model. So in the case of rho going to 0, that means that the internal energy of the system would be 0 because you have no particles in the system, so you have no pairs of interactions. In the case of the density going to 1, that would mean that your internal energy of the system, U over N, would be equal to negative 1/2 EZ rho. Epsilon corresponds to the strength of the interaction. Z corresponds to the number of potential neighbors. The 1/2 corresponds to the fact that I need 2 particles to give me 1 pair of interactions. So effectively this is to prevent double counting. And the negative is such that it's an attractive interaction. So what we're going to be doing is we're going to use this expression here, more or less, that the energy of the system, which is going to be equal to the internal energy, and we can write it a couple different ways, is going to be negative 1/2 epsilon z . So these are just a couple of different ways we can rearrange it. This is going to be the functional form that we'll actually use here. It makes it a little bit more complicated to make it density squared, but when you insert it into the other expressions, it'll actually make the math a little bit easier. Okay, so this is effectively the mean field approximation for the energy of the system. The higher the density, the higher the energy of the system is going to be. Because you're forcing those molecules to be in near contact with one another. So, in terms of our free energy, either Helmholtz or the Gibbs free energy, the difference here is that PV. So in terms of the free energy, we have an expression now for the energy of the system. Now we need to derive our expression for the entropy of the system. We have a starting point. We have our combinatorial relationship. The only problem is, you'll notice that the units are completely different. Here, we've got everything in terms of density, some parameters, and the volume of the system, whereas here, this is not in terms of density at all. So we'll just restructure it so that we can make it so it's as a function of an arbitrary system size. That's the whole point from transitioning from V to rho. So, entropy from the Boltzmann entropy equation is given by the Boltzmann factor multiplied by, the Boltzmann coefficient multiplied by the microcanonical partition function. So we substitute it in, and for this case here, we'll actually need to use Stirling's approximation. Where we have the natural log of the factorial of some value. We approximate it as, and this is actually a really good approximation for greater than 10, greater than 20. So when we're dealing with something on the order of a mole's worth of particles, this is a very good approximation. So if we substitute in Stirling's approximation into the microcanonical partition function, into the Boltzmann entropy equation, we can write it out in a long form. So I'll write it as the entropy over the Boltzmann constant, natural log. So then just to show the steps of how we would do this, so this is going to be V natural log of V minus V minus N natural log of N plus N. Let's see, minus V minus N natural log of V minus N plus V minus N. So without going through all of the rigor, what I'm basically, excuse me, what I'm basically going to be doing, a couple of these things cancel off right away. So like this V here will cancel with this V here, this N will cancel with this N here. And you can sort of start to simplify it down. The ultimate objective though is I'm going to substitute in the density as N over V, do a lot more arithmetic, but the final conclusion is not all that complicated. The entropy of this system is going to be equal to minus KB times by the volume and now we have an expression for our entropy of the system following a lattice model. Now the only thing that happened from this point to this point was just algebraic substitution and then just condensing the equation down to look a little bit more convenient. So if you see on my notes here, it's like, I don't know, taking like 6 steps. Just a little tedious. But nothing more complicated than just algebra and log properties. So one thing to notice about this is that's really kind of a symmetric function. So if rho, the density, is equal to 0, that means that you only have one configuration of the system, which all sites are vacant, which means that you're going to have an entropy of 0. Conversely, if I have my density is 1, all the sites are occupied, again, that goes back to this condition where the entropy is 0 because all sites are occupied. There's only one configuration of the system. So the maximum entropy is going to be at density of 0.5. Because that's going to be the most configurations that the system can have. I think. Actually, I didn't double check that actually is the maximum of 0.5. Okay, so now we're going to put it all together. The free energy of the system, in terms of Helmholtz, is the internal energy minus Ts. Or we can also write that the Gibbs free energy is the internal energy minus Ts plus PV. So if we write out the Helmholtz energy per particle, again, we're trying to get this independent of system size, so we can sort of arbitrarily scale it up to a particular mixture. Okay, I only make one additional substitution. If I divide my entropy by the number of particles, V over N is the reciprocal of density. So I just made one additional substitution there. Right, so 1 over rho is equal to V over N. Same thing. So just a simple substitution there. The Gibbs free energy is just going to be the Helmholtz free energy plus the PV contribution. Oops. Over N. So now that gets us to our handout. So what we've done is we've taken our lattice model to determine the entropy of the system. We've used a mean field approximation for the total energy of the system. Now the reason why we did this is because this gives us so that every single configuration is equally probable, which allows us to do all of our mathematics in the microcanonical ensemble, which makes our lives a whole lot easier. If we want to do this in the canonical ensemble, certain configurations would be less probable. We could no longer use the simple Boltzmann entropy equation. We would then have to use the Gibbs entropy equation, and then consider the fact that you would have effectively a scaled summation. So you would have to then quantify, label, and count every single configuration, and then know what the energy of that configuration was. Or you would have to calculate the degeneracy of every energy level. Possible, but a lot more difficult. This gives us 90% of the way there in terms of the theory. So what we've done here is that our free energy is now only a function of a couple of parameters, the density, temperature, right? These are all intensive properties. So we don't care how big the system size is. We've cleverly rearranged it to remove any details of information about the system size. So now the whole lattice-based model functionality of it goes away. So if we take a look at your handout, it's sort of broken up a little bit, but I'll try and reproduce it on the board as well. This equation is all we need to calculate a phase transition. So the top figure, yours is hard to read, mine's a little bit better. This is G over N as a function of the density. So over here it is 0, so over here it is 1. This is at constant pressure, and they're varying the temperature. So it says here in the legend that the different lines are just shifted arbitrarily for clarity, right? But what matters is the shape. So in this case here, they say they have T boiling point, right? This is the saturation point between the two coexisting phases. Now that occurs if you have a shape of the Gibbs free energy where you have two minima that are at exactly the same Gibbs. And that's exactly what this, if you were to plot this out with appropriate values for Z, epsilon, and temperature, this is exactly the shape of the curve that you would get. So which one of these two is the vapor and which one of these two is the liquid? This is the liquid here. Right. So this would be the density of the liquid, and this would be the density of vapor. Now, this is for T equals the saturation temperature. If the temperature, let's say, is greater than the boiling point, what should the curve look like? What should change? Which one of these should have a higher free energy? And in fact, the way that they did this one here, they drew it down here at the bottom. So T is greater than T boiling point. What will happen is that the vapor, the low density fluid, will now have a lower free energy. Conversely, if the temperature is less than the boiling point, the liquid will have a lower free energy state. That follows the same trend here as what's shown. Now additionally, they also have a second figure that looks at, in this case here, this is the Gibbs free energy as a function of density. They have an additional figure looking at a phase diagram, but as a function of pressure and temperature. So on the left, they have a PT phase diagram, so pressure temperature phase diagram, at which point you hit the critical point, TC and PC. And you'll notice that they have basically what I've reproduced here, but the Gibbs free energy profiles as a function of density based on whether or not you are in the, in this case here, let's see, low temperature, high pressure, this would be liquid, this would be vapor, and this is going to be supercritical fluid up here. So you have 4 reproductions of the different density profiles. And then lastly, we can also look at a temperature phase diagram. What will happen as you get closer and closer and closer to the critical point, these two, right, so this is in equilibrium. So what we're doing here is we're plotting this equilibrium, maybe let's say that's this point here. As you change the temperature, you also have to change the pressure, and eventually you'll reach the critical point where there's only one Gibbs free energy minimum. So this simple, relatively simple stat-mech model balances out the forces of energy and entropy simultaneously. It produces realistic effects in terms of phase diagrams and behaviors. And so more or less, it is the appropriate or the equivalent of a macroscopic cubic equation of state. And indeed, that's going to be our next step, is to reproduce more or less the functional form of the van der Waals equation of state using this model here. Does that make sense or not? Good? All right. So, next step. Let's try and get our model to look like a macroscopic equation of state. Where are we at? So we have a couple of relationships here. We can derive an expression for the pressure relying on exactly the same macroscopic thermodynamic properties. Right, so one of the things about StatMech that I always like to do is get out of StatMech as soon as possible and get into classical thermodynamics as soon as possible. Now our formulation for the Helmholtz energy right here is actually A over N, and it's as a function of density, not as a function of the volume. So we're going to do a really quick unit transformation here. So this is going to be equal to, using the, oh geez, I can never remember. I think this is the chain rule? Okay. So in this case here, we can write that the density is equal to N over V, such that d rho dV is going to be equal to negative N over V squared. We will substitute that up into here, and then we can find that the pressure is then going to be equal to the density squared times by how the Helmholtz changes with respect to density. So if we go through the math, effectively what we'll do is we just need to calculate the partial derivative of this function with respect to changes in the density. And the fortunate news is that it actually becomes a relatively simple expression. And we have an equation of state for our lattice model. So let's contrast this. The ideal gas law for StatMech is oftentimes written like this. We can also, of course, write it as any number of forms we'd like to write it. This is our ideal gas law. Now our van der Waals equation of state is going to be RT V minus B minus A squared. But of course we could also kind of think of this as KBT like so. So, I don't know about you, but when I see these two equations, the equation that we derived and the van der Waals equation, I see a lot of similarities. Because the density is the reciprocal of the specific volume. Meaning that this first contribution here looks sort of like A over V squared. Where in this case here, A would be equal to 1/2 epsilon Z. This one here doesn't look quite the same. We have to do a little bit more work on this one. So what we're going to do is we're going to transform this, and we're going to transform it from density units to specific volume so that we can directly compare our van der Waals equation of state to the equation of state that we just derived using a lattice model. So, if we do so, we can write that our lattice model pressure is going to be equal to minus 1/2 epsilon Z over squared. So right now I just did a simple substitution of taking the reciprocal of the density, which is the reciprocal of the specific volume. And then a little mathematical rearrangement here. We can get our equation to look like this. It's not exactly the same functional form, but I would say it's pretty close. So if we were to look at a comparison, in this case here, we're comparing it to our lattice model. Our attractive potential is basically 1/2 EZ. And for a 3D system, remember, which I live in the 3D world, so I prefer that model. Now the other missing part here is that we of course have the KVT, right? That's shared across the two models. But the difference here is that we're looking at 1 over V minus B compared to this a little bit more complicated natural log function. But as it turns out, if you plot this, if I plot natural log of v over v minus 1, what it looks like is that at a specific volume of 1, so let me do one more thing here, sorry. Density is between 0 and 1, right? So we can have no sites occupied or 100% of my sites occupied. The specific volume is the reciprocal of the density, such that the specific volume has to vary from in between, let's see, 1 to infinity. So this comes here, because the reciprocal of 1 is 1. The reciprocal of 0 is infinity. So the limits have switched here. Oh, yeah. There we go. So what is effectively happening then, if we look at this function, it more or less looks like the same type of a radical function that we would see in the van der Waals equation of state, but instead of it diverging as the volume approaches the excluded volume, in our lattice model, the excluded volume is 1, just based on how we defined it. So more or less, this function here is approximately the same as 1 over v minus b. So in the course of, well, let's see, I'll give ourselves a half hour, we have effectively rederived the van der Waals equation of state, which I think is kind of neat. And we did it assuming more or less the mean field approximation was the biggest connection that we had to do. And that's exactly the same approach that all other cubic equations of state are based on. But instead, in our case of counting up individual discrete pairs of interactions, how the van der Waals equation of state was derived is if I have a particle at the wall, and I assume that there's no pull of the particle going into the wall, and that the pull itself is based on an average density of the fluid pulling back at it. That's the way that the van der Waals equation of state was originally derived. So conceptually, it's very, very similar. Whereas in the van der Waals equation of state, it did it on a continuum basis. What is the mean density of the fluid pulling back on that single particle based on the interparticle attractions? In the lattice model, we did it explicitly saying, okay, now particles can only fall in these exact locations, and that's how we were able to get out a quantitative metric for the entropy itself. But I think that's kind of neat. So one last thing to cover is now that we have an equation of state, we actually have to do something with it. How will we be able to benchmark it? And this is effectively going to be what I'll be writing up as a homework problem for each of you to plot this function and play around with it. We need to tune it. So if I were to draw out a PT phase diagram, let's see, pressure, temperature, real fluids, or at least cubic fluids, sorry, this is PV, PV, looks something like this, right? And we'll say that if we connect the dots here, cancel out the areas, this would give us the saturation pressure at whatever the temperature of that specific isotherm was derived at. Eventually, the properties of the two phases will come closer and closer together. In this case here, this is going to be volume, so it's the reciprocal of density. This is the volume of our liquid phase. This is the volume of our vapor phase. All the other stuff we did was flipped because we looked at it in terms of density. But we can draw a connection between all of these different densities, and we develop ourselves a phase diagram as a function of temperature. Now eventually we'll come to the point where on the PV isotherm, dP dV is equal to 0. Right, in this case here, we have an inflection where it goes, the second derivative changes slope. And this point right here also, the second derivative of pressure is equal to 0. What do we call that point? That's the critical point.
Yeah.
So now what we need to do is we basically need to take our lattice model and determine what is our critical temperature, critical pressure, and critical density. And from that information, we can then benchmark our attractive potential. So, if we do that, we can derive a system of two equations, and we can solve them simultaneously and algebraically. So, from here we can get that the critical density, right, which is the equivalent of the critical specific volume, is just going to be equal to 1/2 the critical temperature is given by this. If we substitute those back into our equation of state, we can derive what the critical pressure of our fluid is. And so on. So now we have a method that we can actually see how well does this equation of state match to real fluid property data. So if I can get my act together, I'll try and find some data. I believe that ideal monatomic gases, noble gases, behave pretty close to a lattice model fluid near the critical point. But I'm going to try and find some experimental data where we can benchmark this to real data and see how well this stat mech theory holds up to, let's say, supercritical or critical I don't know, liquid argon or liquid xenon, for example. I just need to find the PV isotherms for that. But, so every time that you go into sort of like the literature and you find some paper from the 1980s, it's always papers from the 1980s and 70s of physicists going to big, fancy, expensive scattering facilities to measure the structure factor and the radial distribution function of liquid noble gases. They're not doing it just for the sake of doing it. They're doing it to benchmark these types of models. Right? So the ability to do cryogenic gas structural measurements is a way that we can use to benchmark these parameters and sort of figure out what are the fundamental physics that underlie particle-particle interactions. And if I'm going to choose a simple system, I'm going to start off with argon. The reason why argon is always the one that people start off with is because it's abundant in the atmosphere, it's heavy, right? It doesn't float away like neon and helium, right? Those ones just go and float away. Argon is heavy, so it's captured in the atmosphere. It's also bigger, which means that the temperature that it condenses into a liquid at is a relatively higher temperature. And it's not so big, like xenon, that has so many electrons that it becomes highly polarizable, right? The electron field of xenon can slosh around back and forth. So argon is a sort of perfect balance, more or less out of convenience. That's why we do it, as opposed to like liquid neon. First of all, that's really, really, really hard to do the experiment because you have to go to extremely low temperatures. So that's why it always seems like it's liquid argon, because it's the good balance between a simplified system and it's something that's actually not trivial to do experimentally, but easier to do experimentally. Okay, so now if I were to repeat this whole procedure, but in the canonical ensemble, and I were to perform a two-dimensional Monte Carlo simulation, which we'll talk about what that means a little bit more next week. If I were to actually do this simulation and come up with all the possible configurations, and take those configurations and calculate their energy, and then scale the probability of those configurations based on the energy of the system, what I would be doing then is I would be eliminating the mean field approximation. The mean field approximation is saying that all configurations of the system are equally probable. So as it turns out, that overestimates the critical point. So in 3D, with the mean field approximation, the critical temperature is 1.5 epsilon divided by kV. Now this epsilon value here is necessarily going to be very, very small, right? Because the Boltzmann constant here is also very, very, very small. This is the energy between two particles. Not 2 moles, 2 particles. So this energy here is extremely small. So this is the temperature at which the entropy is going to be, and I erased it here unfortunately, right? But if we're kind of considering, if you got in your notes, but this is the temperature by which that the energy of the system cannot overcome the entropy. The entropy will dominate and it'll be a supercritical fluid. It won't be a condensed phase. Now if we were to repeat this here, if we were to repeat this effectively in the canonical ensemble, meaning that we are not using the mean field approximation, we are actually organizing, tabulating, and calculating all the configurations of the system with all of their specific energies, we'll find that the critical point is actually a little bit lower, 1.12 epsilon over kV. So in a sense, this really quick, in 50 minutes, we've rederived the van der Waals equation of state, or similar appropriate one. With certain simplifications, we already have the parameters to benchmark the equation of state to see how well it holds up for fluids of different complexity. And even with all that complexity, it's still pretty good in terms of a back-of-the-envelope calculation type StatMech model. Now, this approach that we did here is more or less the basis for a lot of mixing relationships for continuum scale thermodynamics. Has anyone ever heard of Flory-Huggins theory? So you've heard of Flory-Huggins. Flory-Huggins is a lattice-based StatMech model for activity coefficients of polymers, just based on geometric considerations that polymers are chains of molecules connected to one another. So a lot of theories that we use, those relationships that are built in Flory-Huggins theory, those are implemented into more advanced modern equations of state. So these approaches here, these functional forms, this is the basis for all modern equations of state. It may not seem like it, right? But effectively, this functionality here, with more advanced models, a little bit more so. This is going to be the formulation for all of the modern and accurate equations of state that we have access to. The challenge is that for the condensed phase, when we have a really high density of particles, even this is still insufficient to give us accurate reproductions. So we have more advanced models, like the SAFT equation of state, the PC SAFT equation of state, and then ultimately molecular simulations are the one where you just say, you know what, I'm just going to put it all in a box and simulate it on a one-by-one basis. It's very slow, but it's the most accurate estimate that we have for fluid properties itself. And even still, those aren't particularly accurate. But the reason why we like to have these equations of state on a continuum scale perspective is if you're trying to do lots of calculations. Let's say you're trying to model and optimize a distillation column or a reactive distillation process, or flow through porous media. You want to know, is gas dissolving in my liquid? If I'm producing oil reservoirs, at what point of pressure temperature does my gas volatilize and it changes it from a one-flow region to a two-phase flow region? So that's why having these equations of state are really important to benchmark those there. All right, any questions? So hopefully this was an interesting lecture. I find this model to be really compelling because it basically, again, is another connection or a bridge between the classical scale and the microscopic scale or the statistical scale. I think it's really cool that we can basically rederive a cubic equation of state using two different methods overall. All right, have a good weekend. Reminder that Tuesday is the day that your selections are due for the paper, for the data. If you go onto Canvas, you'll see that Tarek's name is on there with a link to his paper. So if you can also, when you send me your paper, send me the link to the online abstract so I can get the DOI number. And that way it's easier for you guys to all double check. So for example, Tarek chose the benzene toluene system. Now you can still potentially choose the benzene toluene system if you can confirm that it's at significantly different temperatures and pressures, but in this case probably not. But that's why I've included the link so you can click on the actual link, look at the actual data, and confirm if you actually choose something different. All right, thanks.